Welcome to the lecture 31 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. This is the first lecture of 7th week. In this week, we will mainly focus on solar cell modeling part 2. It includes some important physical models for solar cell simulation. In last week, we discussed the modeling of solar cell, and in that we have derived the expression for photocurrent considering the position dependent generation rate, and also we have described the spectral response, which is a function of wavelength, different types of scattering mechanism followed by some mobility models we have described. Also we discussed about the carrier saturation velocity at a high electric field. In this week, we will continue to the electrical modeling, but in this week we will mainly focus on models for some important physical parameters. Say for optical modeling means when a light is passing through a multi-layered dielectric interfaces, how the light intensity changes due to different interfaces. Also different types of tunneling mechanism of carriers, particularly if there is a metal semiconductor junction with a Schottky barrier for characteristics. Also some band tail states and recombination models will be discussed in this week. But in this first lecture, we will focus on band tail states in a amorphous semiconductor material. And also the near band edge absorption will also be discussed in this lecture. The band tail states. We know in a perfect crystalline semiconductor, atoms are arranged in a periodic lattice, perfectly periodic structure. And this long range of periodicity allow us to describe electrons using Bloch function or Bloch theorem. We derived the expression for density of states in a perfectly crystalline semiconductor material in some earlier classes. And there, instead of a actual potential profile, we considered the square shape potential due to atoms. And we obtained the density of states for the semiconductor material, and here we have seen that there are two band edges. That is a conduction band edge or called conduction band minima, and another is valence band maxima. In between these two edges, there is no energy states exist. And these sharp band edges occurred in a crystalline periodic structure. Say for example, if we redraw the band diagram and the density of states for crystalline semiconductor material, it looks like this. Suppose this is the conduction band edge, or this is called say conduction band minima, and this is valence band maxima. In between, there is no energy state available. But in the band, valence band, there are closely spaced energy states which forms the band. Similarly, in conduction band also, the formation of bands, so very closely spaced energy states, they form the band. But in between, there is no energy states. This is called forbidden gap, or EG, is a band gap. And these two band edges, conduction band minima and valence band maxima, they are well defined in a crystalline semiconductor. That means we have assumed that atoms are arrayed in a regular fashion. Say these are the atomic array in one dimension. So this is the potential we have considered. If you remember, now this forbidden gap has zero states in case of perfect crystalline semiconductor. But in case of non-crystalline, it is an amorphous nature semiconductor, say amorphous silicon or other materials, say oxide materials, oxide semiconductors widely used for solar cell, say zinc oxide, ITO, AZO, that is aluminum doped zinc oxide. These are all amorphous in nature. It is very difficult to obtain the material having perfectly periodic array of atoms. So there are irregularities in the atomic array. And due to these irregularities or disorder, now the band position will change from the crystalline semiconductor. And this will create states called band tail states. Why the term tail? I will explain. And in amorphous material, there is a short range order. Short range order means in amorphous silicon, say there are some grain boundaries. Grain boundaries means you can find some region where the periodicity of atoms are present, but nearby another region, they are also atomic array are periodic, but in a different direction. So these are called some small grains, and they have some grain boundaries. So one region and another region, they are separated by some boundaries, assumed boundaries. This is called grain boundaries. So this looks like this. Suppose you have a amorphous silicon. So suppose this is a grain boundary. So in this particular grain, suppose atoms are arrayed in a regular fashion. But in nearby region, so atomic array will be, say, in a different direction. So here the array is along this. These are the arrays. But here orientation of array direction is different. So these are called grain boundaries. Similarly, so there may be grain boundaries. So these call grains, and these are the grain boundaries. So we can say short range order. So in a short range, atomic array is in order or periodic. And due to this short range order, actually this is called total structural disorder. And this modifies the potential seen by electrons. In perfectly crystalline nature, potential seen by electron is a periodic in all dimension. Just like here, you see this is the thing throughout the material or throughout the crystal. But in case of amorphous material, due to short range order, electron realizes the potential which is not same in all direction. So ultimately, this leads to localized states. Localized states means these states extends into the band gap and near the band edges. That means now some energy states will be available near the edge and within the forbidden gap. Say, let us mark it by a different color. Say here, suppose these are the new bands, energy bands, which exists for amorphous material, and these states are localized in this sense. Carriers in these states cannot conduct freely, just like a conduction band. So carriers are localized or confined within this band. From one state to another state, carrier may move by a different mechanism called hopping mechanism or other thermionic emission and recapture emission, etc., but not like a free movement for electrical conduction like the carriers in conduction band. That's why its name is localized states. So evolution of these localized states is due to the disorder in the structure. And these also in the band gap. That means earlier band edge was conduction band minima and valence band maxima. So in between there were no states, but here these states may exist in the band gap. And these are called Arbach tails or band tail states. That means if we now consider the density of states for a perfectly crystalline semiconductor, it looks like this. Suppose there are two band edges. One is, say, conduction band minima, say conduction band minima, and another is valence band maxima. Now you remember the plot of density of states looks like this. This is proportional to square root of energy, E minus EC. This square root, this is proportional to the square root of E minus EC, and this is square root of EV minus E. And there is a clear edge. So in between conduction band minima and valence band maxima, there are no states. This is the density of states, rho C E, and this is rho V E, and here it is energy. Along y-axis energy is plotted. This is proportional to square root of EV minus E, and this is proportional to E minus EC. EC is nothing but this conduction band minima energy, and EV is valence band maxima energy. Now, in case of amorphous material, due to structural disorder, some states are existing in the forbidden gap near the band edge. Then how the density of states will modify? Density of states has a tail that will not become 0 here. So it is tail, it has some tail. So let us see how it looks. This, instead of going to 0 here, so tails looks like this. So these tail states and the modification of density of states due to these extra energy states is called band tail states. Band tail states. And generally these states has a exponential nature, that is exponentially decaying function. So now the density of states expression, what we discussed earlier, that expression is valid only for perfectly periodic crystalline semiconductor material. But for amorphous nature of material, the density of states will be having a different forms. And the band tail states decay exponentially into the forbidden gap from the conduction band edge and the valence band edge that I have already mentioned in the figure. And this drawn in a different colors to make it different from the density of state of a perfectly crystalline semiconductor material. Now structural disorder is the reason. Also the thermal vibration. Thermal vibration means at room temperature. So vibration of atoms creates some wave, and that lattice wave has a particle equivalent called phonon that we have already discussed. So if we increase the temperature, the nature of phonon or nature of lattice wave will also be changed, and this phonon induced disorder is also contribute to these band tail states. So these band tail states are coming from not only the structural disorder, also from phonon induced disorder. And these energy state broadening or the broadening of density of states inside the forbidden gap will result in a absorption tail, because in case of semiconductor material the band gap is Eg, and we know the condition for absorption was H nu must be greater than is equal to Eg, band gap energy. So the photon with energy greater than the band gap energy can be absorbed by a material. But here ultimately the gap between the energy states becoming low from Eg. So we can have that some lower energy photon now can be absorbed by amorphous material. That means in case of semiconductor material there is a sharp drop of absorption spectra at lambda c, there is a maximum wavelength, but that wavelength now extended beyond lambda c in case of amorphous material. So that is a tail in absorption spectra, and that tail is called also Arbach tail. So since the energy states is extended within the forbidden gap, so some lower energy photons now can also be absorbed by the material, and that will change the absorption spectra, and there will be a tail like nature in the absorption spectra. Instead of sharp fall at critical wavelength, or sorry, at maximum wavelength. They are beyond maximum wavelength as per the formula h nu is equal to Eg calculated, that beyond that lambda also some absorption is observed. Lower energy means higher wavelength. So some low energy photon can be absorbed, that means some higher wavelength photons can be absorbed. So there is a tail also called Arbach tail. Now, how can we describe the band tail states mathematically? So there is a derivation, but we don't go to that derivation in detail. There are several models for deriving the expression for density of states. In case of amorphous material, it is very difficult because you have to go through some statistical approach or ensemble approach, otherwise you cannot get that value. So there is a huge number of disorder is observed in case of amorphous material. So this is really difficult. Anyway, so exponential decay of these band tail states is observed, and it is obtained from all types of calculations. So how it looks? So the exponential density of states distribution in the band tail energy is modeled as rho Ct. Rho stands for density of states, C is conduction band, and T stands for tail states. The rho Ct is the tail state density of states below conduction band. That will be Nc. Nc is the effective density of states in a conduction band, exponential minus Ec minus E by E0C for E less than Ec. Be careful, the energy E less than Ec. And this Ec minus E, that is how it below from the conduction band edge, that will determine the value, and which is coming with a negative sign that indicates it decreases. That's why if you see the plot, it decreases exponentially, and it is shown in the last slide. And for rho v t, that is a valence band tail states, will be again the nv exponential minus, but here E minus EV by 0V for E greater than EV, and it is following the same nature like EC minus E in case of conduction band and E minus EV for valence band, but with the exponential negative nature. But in case of semiconductor material, the density of states is proportional to the square root of E minus EC and square root of EV minus E for E greater than EC. So parallelly, if we write, so rho C, that for states, that is proportional to E minus EC for E greater than EC, and rho V E, that is proportional to EV minus E, this is E less than EV. This is the formula for states we have described. Now, the rho Ct, rho Vt, already I have discussed, this is the density of states, but what is the value of E0C and E0V? This is very important. And ECV, already I told, this is a band edge. Now, E0C and E0V, these are characteristic Arbach energies. This is nothing but a measure of tail width, and this value is taken different for different materials. Say for amorphous silicon, it varies from 50 milli electron volt to 100 milli electron volt. Also, it is a variable, because if you develop amorphous material by a different mechanism and using a different machines, you may have a different values of E0C because of different structural disorder mainly. Even if you develop a same recipe, if you develop the amorphous material by using same recipe in a particular machine also, it may vary from time to time because of structural disorder cannot be same for every time you develop or you deposit that material. So that's why there is a range 50 to 100 millielectron volt. And again, this value is determined like a fitting factor or fitting parameter by observing the Arbach tail or absorption spectra, etc. There are techniques, but it is not a fixed value. And always it has a ensemble approach, ensemble average approach, a statistical approach to extract this value. Say for amorphous silicon, this value is noted. For other material, other amorphous material, this value will be different. And what it is measure of tail width. So this is the very important. Again, if we draw here, say this is for, but this exponential decay and this width of this tail state is taken as an average value or a particular value, particular E, it is taken. So this, sorry, this is E, this is rho C, E, this is rho V, E. So the exponential nature of these band tail states is different from the nature of density of states for E greater than EC. Now absorption, I already mentioned that due to presence of these tail states, some low energy photons can also be absorbed by the material. And optical absorption coefficient near the band edge also shows the exponential decay, because absorption takes place pair of states. Means if light is incident on a material, electrons in the lower energy state may get additional energy and this may transit to a higher energy state. So a pair of energy states are involved. So as the density of states exponentially decay in the band tail states, so absorption in the band due to band tail states also will be exponential decay in nature. So that's why it is mentioned that the band edge absorption is also show the exponential nature. And the alpha E, if we say the absorption coefficient alpha, this is a function of E because there is a difference between two energy states, E1 to E2. So a pair of energy states are involved. So some alpha 0, this is some prefactor, exponential minus Eg by Eu for E less than Eg. Be careful, this E less than Eg. For energy below band gap energy also can be absorbed. And Eg is optical band gap. Optical band gap means EC minus EV. This is called Eg. And EU is nothing but Arbach energy. And this is a slope of exponential absorption tail. And this can be obtained by an inverse relationship, that is EU, that is due to the 1 by E0C plus 1 by E0V, that is a width, tail width for conduction band tail states and tail width for valence band tail states. There may be different value, they may be same value, and they are related by this formula. So you can take the EU, that is the Arbach energy, which determines the slope of exponential absorption tail. So, and alpha 0 is a prefactor. So ultimately, what I want to mean, the band tail, how it looks in absorption spectra. If you remember the absorption spectra for a semiconductor material, it suddenly drops to a particular value called lambda max. Lambda max corresponds to h nu min, nu minimum. So let us draw the nature of absorption spectra. If you remember, this is the general nature of absorption spectra. So this is lambda max. This is wavelength lambda. This is say alpha, centimeter inverse or meter inverse, whatever, or other material say this. So material 1, but there is a sharp decay this value at lambda maximum. Lambda max corresponds to nu minimum, and nu minimum is determined by h nu minimum is equal to Eg, and you know the thumb rule formula, that is lambda max in micron is equal to 1.24 by Eg in electron volt. That also can be calculated. But for amorphous material, due to presence of states in the forbidden gap, that is tail in the absorption spectra also present. It looks like this. So instead of sharp falling, the spectra will be looking like this. This tail, absorption tail. Okay. Similarly, say here we use a different material. For this material also we have a so this absorption tail is due to presence of this. It is observed in case of amorphous material. So during simulation, whenever we will be discussing or we will put the amorphous layer in solar cell simulation, absorption also will be look like this. Now, one concept is called mobility edge, which is very important concerning the amorphous nature. Mobility edge, basically it wants to mean the band edge. I mentioned that the carriers in the conduction band, they can move freely, or carriers in the valence band also can move freely, but carriers in the tail states, that is in the forbidden gap, they can move by hopping mechanisms, by some emission, thermionic emission mechanism, etc. So they cannot move freely. That's why the conduction edge also can be called as a EC and EV. This is the conduction edge or called mobility edge, because mobility is associated with the drift velocity of the material. So that's why the mobility edge concept is introduced. And the mobility edge for a amorphous material will be an extended states with a critical energy, say E critical for conduction band or EV critical for valence band, above which the carriers can move and take part in conduction by hopping mechanism or other thing. And below that energy, states are localized, states are considered to be localized. That means carriers cannot move freely but can contribute hopping conduction. That I want to mean, suppose you have, this is the band edge, EC and EV. If we consider, better to write in a, draw in a red color, red is indicating for crystalline nature. The valence band, conduction band is there. Suppose a tail state lies very close to the EC as drawn by black color. Similarly, a tail state suppose very close to the EV. And in this state may be treated as non-localized, because if carriers from conduction band captured by these states captured, and then they can easily emitted due to thermonic motion, so they may be treated as a edge of the conduction, that is edge of the mobility. So it has a certain value of critical value, E critical, below, above which, so this is the critical edge, this is the critical energy, EC critical. This is suppose EC critical. So above this energy, whatever the states, they may be considered as a non-localized. Similarly, here also EC critical, EV critical. So all the states within this range, from EV to this range, they can be considered to be non-localized. That means if carriers are present there, they can take part into the conduction of electricity. So these are called mobility edges for semiconductor, amorphous semiconductor material. But if some states are below these critical edges, in these states, if carriers in these states exist, so these carriers may hop or may go to the next states by hopping mechanism. So critical energy, EC critical for conduction band and EV critical for valence band, these are two very important, and these are called mobility edge. This is the concept of mobility edge. And for conduction via electrons in the conduction band tail is represented as, say, sigma t almost equal to exponential minus EC critical minus EF by KT. EF is the Fermi level. So the conduction due to the carriers in the tail states above critical level, above critical value, sigma, the conductivity, is governed by this formula. But in the conduction band, that sigma value, we know n mu q, q n mu n plus q into p into mu p, that we have also discussed. But here the conductivity sigma, which is also temperature dependent, is exponential minus E critical minus A by KT. More and more the difference, less and less will be the conductivity due to the presence of negative sign. This sigma t expression also coming from the basic exponential decay of the tail states. Now impact of band tail states, what are the impacts? What can be the impact? We have already seen that absorption spectra has a tail. Also in the conduction there is a change. So some conduction now may take place due to the carriers present in the tail states above critical level or above mobility edge. So electrical transport, tail states cause carriers to localize. This results in conduction via hopping or thermally activated transport, or if the carriers are present in the states above mobility edge, they can take part in the conduction. Optical absorption, exponential absorption tail below the band gap, that is above the lambda max. So this ultimately affects the device behavior, mainly the stability in a amorphous semiconductor based devices, say solar cell, thin film transistor cells, etc. And also this may cause a leakage. So we have discussed band tail states in a non-crystalline semiconductors, and these states are exponentially decaying in nature, and these states are called localized states which extend into the forbidden gap, and this is mainly due to the structural disorder and also due to the phonon induced disorder. And states are basically described mathematically by an exponential density of states expression, which is different from the expression for density of states in crystalline semiconductor material. And these tails also called Arbach tails. It affects both optical absorption and charge transport and introduce the concept of mobility edge. And the energy of photon less than band gap energy can also be absorbed by amorphous material. These are the references you can follow, or you can study, or you can go through for detailed analysis and derivation if you want for exponential decay density of states for band tail states. Thank you.